Hello guys, hope this video will be very interesting and very informative for you. So please proceed to the video. In this session, we will study the problem of implementing a 4-bit adder on Verilog, and the FPGA used will be Nexus 4 board. The main features of our adder circuit are it will take two 4-bit numbers as input, and it will use 8 switches definitely, and it will result a 5-bit output. 4 bits used will be used as a sum, and 1 bit will be a carry. So we will display 4 bits on a 7 segment display, and the carry bit will be displayed on a LED. So this is the Nexus 4 board with its main pinout and as shown in the diagram. So the interesting things for us, or we can say our interest things, are these 16 switches and the LEDs above them, and also we use a 7 segment display from these 8 7 segments, and one LED from this area will be used in our adder circuit. The other thing, to get the details of other things, you can refer to the Nexus 4 reference manual. So we have two 4-bit numbers which are to be added, and therefore we have 8 inputs from the host system to the compute engine. Then we have two switches as control switches and control signals, and one is known as enable and one is known as valid signal. The difference between the enable and valid signal is that after you enable the FPGA, after you enable the enable signal, after you set it high, the FPGA will read input from the switches, and whereas upon turning the valid signal, the FPGA will calculate the outputs and display on the display system. So our display system has, as I have told you already, it has a single 7 segment display as a sum and one LED as a carry. So on the board, what are we using? We are using the rightmost switches as a first input, 4 switches as a first input, and then the next 4 switches represent the second number, and on the left we have an enable signal to turn it on or off, and then the next is the valid signal. Addition of 4 numbers gives us 5-bit output. Therefore 7 segment display is used to display 4-bit sum, and the multicolor LED is represented to represent the 1-bit carry. So we are using this min assignment for our adder circuit on the Nexus 4 FPGA. So the first set of column represents the inputs from the board, and the next set of column represents the display outputs, and the last column represents the control signals and carry out signal. So you can see that these are the pin numbers that we are going to assign in the Vivado project when we will see it on the next tutorial session. So for more simplicity, we have divided the given Verilog code into these sequence of commands. Means read inputs, it will be there will be a first phase of reading the inputs and then displaying the inputs as LEDs, and then control signals will be encountered, and after that adder circuit will be used for the calculation of the on the inputs that are given to us, and then we have a phase of displaying the results. So I believe that the code is provided is self-explanatory and is as shortest as possible and as simplest as possible. So you can go through the code and you can have main simple idea. So this is the 4-bit addition table. It contains a superset of all possible answers of adding two 4-bit numbers. So we move forward to the step-by-step design and synthesis and implementation of adder circuit on the FPGA. In this session we will be having a complete step-by-step design, synthesis, implementation and testing of an adder circuit on Nexus 4 board. So I believe that you have installed Vivado on your computer. Therefore click on the Vivado icon at your desktop and or in start menu, and it will be open as follows. This is the main interface, starting interface of the Vivado. Now click on the create project under the quick start, or go to file, there is another option, or go to file, project and new, then you can have the same option over there. So click on it, and on the new project wizard, after clicking it, you will be having to enter the project name and location. So I am naming the project as Adder Interactive. I am adding it. You can have any name of your own. And the path that I want to give it is something in my system that is already over there. So I will like to have this path for my Vivado project. So I believe that there is no project with the same name, so I have to give it this path. It will also create the subdirectory of the same name. So press next. Now select the project type to be the RTL and select next, and it is already RTL, so we have to select next. On the add sources window, click on the create file and type the name of your source file, and I am creating it as a core, and it will be as a default as a Verilog file, so I have created it as a Verilog file. Now once we created it, we have to press the next. In the add constraints, we don't have to add any constraint file at this time, so just we have to click the next. So we have two options in this selection of the board or selection of the part area. So in case you have the board files of the Nexus 4 board, you can select the Nexus 4 board from this list or by searching from there. If you don't have installed, as I have I don't have installed the Nexus 4 board in this machine, so just I will type the part number of the FPGA that is being used, which is XC7A. I am showing you here, just pasting it. This is XC7A 100T CSG 324. So speed gate is -1, so I am selecting this FPGA part. So just after selecting it, just click the next. Now you can see the Vivado project manager interface. After first of all I have to finish it, then we can have a project manager interface. So the code file will be generated as default. So you have to just open this file and just type the code that will be written, that is to be written on the board. So here is the interface. I am just minimizing the other things just to show you the code area. So we have this area for the code. So I have written the code already with me. So I will just copy and paste this code, and I will explain it simple single bit to you. I am selecting all and I am just replacing the code. So this is input output interface for the code. So a clock will be the input, and enable signal and valid signal will be input, and the switches will be input, as I have discussed in the introduction section. Then we have LEDs for enable and valid. It will show the status of the enable and valid, and the carry out, it will also show the if there is a carry in the result, it will show the carry out LED. This is also an LED, and these are the 8 LEDs for the switches, input switches, and these are the 7 segment display signals that are known as anode and cathode. So this area is to read the inputs from the board or from the switches, and this area of the code is for the display of inputs, and inputs means in the form of LEDs that are just above the FPGA switches. So this area is for the control signals, and this area is for the adder circuit to add or not in case of valid or not, and this whole area is for the display of the adder result. This is very simple, and we can say 60 to 70 lines of codes which are doing all the interactive addition. So after pasting the code, now we have to just save it, and after saving it, and we have to just run the synthesis, which is in the flow navigator. This is flow navigator area. So it is the code is under synthesis. Once the code is successfully synthesized, it will show the success dialog. This is shown over here. I have to wait for a few minutes. Then I have we can have to open the synthesized design and then click OK. To open, because we have to enter the pin assignment for the board. So as we have the synthesized design opened, so we can see something from this area, that if we want to see how our RTL seems like, so we can open the elaborated design from the RTL analysis and see the schematic. So I want to spend some time to see the schematic, because this is the first project for you, so you have an idea of how our schematics look like. So this is our schematic of the adder circuit. So you can see those input output signals that we already discussed with you. So it's okay. We just have to move to the pin assignment. This is IO planning. This is called IO planning. So we have to select it and assign the pins that we already told you about in the last slides, that we have to assign some pin names, and we have to assign some default values for the voltage, etc. So first of all, I will select the clock the pin name for the clock is P3, and its voltage standard or IO standard is LV CMOS 333. All the signals in Nexus 4 board follow the LV CMOS 333 as the IO standard. So we have to just turn all the signals to LV CMOS 333. So let me complete the other pin assignment. So the pin assignment has been completed for all the 38 pins that we used in this project. So we just have to press the save button over here and give it file name with, we can say, core X. I will say it's core X. So this is constraint file for the board. So after we have planned the inputs and outputs, we have to open the synthesized design, and from here we can edit the timing constraints. So here it is the edit timing constraint option. So just click it, and in this area you have to assign the clock just by double clicking on it, and it is asking that synthesis design is out of date, so we have to re-synthesize it with the updated design. So just wait for it. Give here the clock name, and we have a clock name as CLK, and its period is 10 and 5 false. This is everything, leave it to that. So press OK. Now click on the run implementation. So by pressing the implementation, we can see the resource utilization of the design and other power calculations, etc. So we just have to wait for the implementation to get complete. The status of the implementation or synthesis is shown at this area. You can see it is running the synthesis design. So just wait. You can see the implementation is completed. So we just have to open the implemented design. So just click here, and we can see the resource utilization and the power values from the project summary. So we will click on the project summary, and we will enlarge it. We will have you can see we have 11 watt of the power for our this design, and the graph for our utilization of sources, or we can have a table of the utilization of sources here, in which we are using 11 LUTs and 24 flip-flops and 38 IOs, and global buffer is single one. Now in the program and debug menu of the flow navigator, this is flow navigator, and we will go to the program and debug menu, and we will just click on the generate bit stream. It will generate the bit stream for our project for the Nexus 4 board. So it will also take some time. This is running the bright bit stream, so we will wait. Now you can see we have a bit stream that is successfully generated. So just we have to select the open hardware manager and click OK. In this time you have to connect your FPGA board to the computer. So I have also connected my FPGA board to the computer. So I am just watching it. So After opening the hardware manager, we have to just click here to auto connect, or we can have open target option from here. So we just have to click the auto connect and it will connect to the board. You can see the board has been connected over here, and it is showing the status of not programmed. So we can program it by clicking on this, or we can have a menu, and in this menu you can click on the program the device. So just we will click the program device, and the pop-up will appear in which core.bit file is already loaded. So we just have to click on the program, so it will program the core bit stream into the Nexus 4 board. So the status is changed to programmed. Now we are moving to the phase that is testing phase, and we will show you the video demonstration of the board, which is Nexus 4 board, in short while. This is the Nexus 4 board which is running the adder circuit, and as we have already told you that these 4 switches are used for the first input, and the next 4 switches are used for the next input, and the leftmost button or switch is used for the enable, and the next one is used as a valid signal. So first of all, I turn on the inputs. So the circuit is not reading the inputs because we have not enabled it. So first, once we enable it, it will read the inputs. Enable is high, and the 3 inputs are high, so it is giving us the 3 LEDs that are turned on because it is reading the inputs. So it is not calculating the output because the valid signal is not high. So we just have to turn it high so that our result is displayed on the LED. So because the first number is 7 and other number is 0, therefore the total sum will be 7. So once we turn it high, the second number from the 5th button, so it will have a 1 input, then 1 plus 7 will be equal to 8. So in case I turn the other switches of the second input number high, the output will be E, because we have 7 plus 7, 14 will be equal to E. If I turn all the inputs high, it will be equal to 15 plus 15, 30. So the carries LED, that is blue LED, is turned on, and the output of our sum is E. So 1 E is the output of our 4-bit adder in this case. So you can play with many values, and you can see the results which are you can verify from the table that was given to you in the demonstration. So thanks for watching. Hello guys, hope you have enjoyed this video, and if you like our content, then please subscribe our channel, and in case of any help you can contact us anytime. Thank you so much.